In the final accounting of the cosmos, what becomes of a fire? Does it simply fade, leaving behind a ghostly cooling ember? Or is it consumed by a darkness so absolute, so profound, that the very memory of its light is erased from the universe? On your screen are two endings, two separate testaments to the conclusion of a story told in fire and fusion. One is a diamond, a single solitary point of defiant light, the crystallized heart of a star that once burned like our own Sunday. It hangs in the velvet void like a celestial tombstone, impossibly dense, fantastically hot, yet serene in its finality. This is a white dwarf, the universe's most exquisite ghost. It is the last stubborn word in a billion-year-long conversation, a monument built from the ash of a nuclear furnace, shining not with new fire, but with the profound residual heat of a life lived in spectacular luminous glory. It is the embodiment of matter's refusal to surrender a final triumphant stand against the crushing emptiness of space. Now let your eyes drift to its companion in this cosmic diptych. There is no object here, only its terrible, violent absence. You see not a thing, but the consequence of a thing. You see a swirling, screaming vortex of superheated gas and dust, a maelstrom of light being tortured and torn asunder as it spirals towards a point of infinite disappearance. This is the accretion disk, the death cry of inbound matter, and at its silent, invisible center lies the universe's ultimate predator, a black hole. It is not an object in space. It is a place where space itself has given up, where time has been broken. It is a puncture in the very fabric of reality, a gravitational wound from which nothing, not even light, can escape. If the white dwarf is matter's last stand, the black hole is gravity's final, undeniable, and eternal victory. These two cosmic spectres, one a beacon of what was the other, an abyss of what will never be again, seem like perfect opposites, sworn enemies in the cosmic saga, but they are not. They are family. They are kin. They are two children of the same parent, born from the same process, the death of a star. They represent the two roads that diverge at the end of a star's magnificent life, and the journey we are about to embark upon is to understand why. We will venture into the heart of this profound cosmic choice, a choice made not by chance or by will, but by a single unforgiving number, the mass a star carries at its birth. This is the story of the ultimate gravity battle, a conflict that dictates the fate of galaxies, the creation of elements, and the very architecture of our universe. It is a tale of two destinies, written in the language of physics, and it all begins with the most fundamental question of all: what truly happens when a colossal burning star finally dies? To understand the end, we must first appreciate the life. For billions upon billions of years, a star is a miracle of balance. It is a celestial gyroscope spinning on an axis of perfect tension. From one side, there is the relentless inward crush of gravity. Imagine the weight of 1,000 Earths, 1,000,000 Earths, a quadrillion tons of hydrogen and helium, all pulling, squeezing, compressing everything towards a single central point. This is gravity in its most primal form, the force that gathers dust into worlds and worlds into suns, the great shepherd of the cosmos. Left unopposed, it would simply collapse the star in an instant, a catastrophic implosion into a cold, dark point of failure. But it is not unopposed. From the star's core, a challenge arises. The immense pressure of gravity ignites a furnace of unimaginable power. This is nuclear fusion, the engine of the heavens. In the star's heart, where temperatures reach millions of degrees, hydrogen atoms are forged into helium in a continuous, violent alchemy. Each fusion reaction releases a titanic burst of energy, a wave of photons and radiation that pushes outward with ferocious force. This outward pressure, this constant explosive exhalation of light, is what fights gravity to a perfect, elegant standstill. The star becomes a sphere of incandescent gas, held in a delicate truce. The inward crush of gravity is precisely matched by the outward fury of fusion. For eons, this equilibrium holds. The star breathes a slow, steady pulse of light and heat its long life, a testament to this grand cosmic arm wrestle. Our own sun is engaged in this very struggle right now, burning through 600 million tons of hydrogen every second just to keep the crushing weight of its own existence at bay. It is a life of unimaginable violence, yet from our distant perspective, it is the source of all stability, the anchor of our world, the reason for warmth, for water, for life itself. But this celestial balancing act cannot last forever. The star's life is fueled by a finite resource. The hydrogen in its core, the primary fuel for its nuclear engine, is not an infinite well. It is a reservoir that is constantly inexorably draining away moment by moment over millions or billions of years. When that fuel begins to run low, the star's long, stable adulthood comes to a close. The balance begins to falter. The battle, once a stalemate, is about to enter its final cataclysmic phase. Gravity, patient and persistent, begins to gain the upper hand. The core, no longer supported by the full force of fusion, starts to contract under its own immense weight. This contraction heats it further, igniting the remaining shells of fuel in a desperate last-gasp series of reactions. The star, its internal structure now in chaos, begins to swell. Its outer layers balloon outwards, expanding to hundreds, even thousands of times their original size, cooling as they go. The star transforms into a red giant, a bloated, dying ember that engulfs any planets unfortunate enough to orbit too closely. This is the twilight of a star's life, a magnificent but terrifying spectacle of impending doom. And it is here, in this final critical moment of instability, that the star's destiny is irrevocably sealed. The path it takes next, whether towards the serene afterlife of a white dwarf or the terrifying oblivion of a black hole, depends entirely on the mass it was born with. Mass is the sole arbiter. It is the judge, jury, and executioner. It is the only variable that matters in the final cosmic equation, the tyranny of a single number that separates a quiet demise from a universe-altering cataclysm. Let us first follow the path of the common star, the lightweight. Stars like our own Sun, and up to about 8 times its mass, are destined for a relatively gentle, though no less spectacular end. As the red giant phase reaches its conclusion, the star's core, now composed of the carbon and oxygen ash from its helium-burning stage, can no longer generate energy through fusion. The engine is dead. The star's grip on its own outer layers begins to weaken. Pulsating with violent convulsions, it begins to shed its skin. Great billowing clouds of gas are pushed away from the core, drifting out into the interstellar medium in a series of final breaths. This expanding shroud of stellar material, illuminated by the hot exposed core, creates one of the most beautiful objects in the cosmos, a planetary nebula. It is a misnomer, having nothing to do with planets, but its appearance through early telescopes was that of a faint, ethereal ghost-like disk. It is the star's swan song, a final, fleeting work of art painted across the canvas of space with ionized gas and light. But what of the core left behind? The stellar heart, here gravity makes its final move. With no fusion to oppose it, the core collapses under its own staggering weight. A mass comparable to our entire sun is squeezed, compressed, crushed down into a sphere no larger than the Earth. The density becomes almost incomprehensible. A single teaspoon of this material would weigh several tons on our planet. The atoms themselves are pushed so closely together that their fundamental structure is broken. The electrons are stripped away, forming a kind of super-dense electrically charged sea. And it is here that a new force enters the battle, a strange and powerful rule from the realm of quantum mechanics. It is called electron degeneracy pressure. You can think of it as the universe's ultimate rule of personal space for particles. The laws of quantum physics state that no 2 electrons can occupy the same state in the same place at the same time. As gravity tries to crush the stellar core into an even smaller space, the electrons resist. They push back with a tremendous outward pressure, not born of heat or fusion, but of a fundamental property of matter itself. They are saying no further. This quantum pushback is powerful enough to halt the gravitational collapse completely. A new, permanent equilibrium is reached. The star is now stable, no longer producing energy, but held up against its own gravity by this quantum scaffolding. This is the birth of a white dwarf. It is matter's last stand, a final stubborn refusal to be crushed into nothingness. It emerges from the ashes of its former self, fantastically hot, glowing, with the residual heat of its collapsed core, a brilliant white light that will take trillions of years to fade. It is a cosmic diamond, a city-sized crystal of carbon and oxygen, the beautiful, enduring corpse of a once mighty star. This is the fate awaiting our own sun in about 5 billion years. Our star will die, but its heart will go on a silent, shining monument to the life that once thrived in its light. But what if the star is not a lightweight? What if it is a true cosmic titan, a behemoth, born with 10, 20, or even 50 times the mass of our humble sun? For these leviathans, the story is not one of gentle fading. It is a saga of violence, fury, and a death so spectacular it can outshine an entire galaxy. Their lives are short and fast. Their immense mass creates crushing pressures in their cores, causing them to burn through their fuel at a ferocious rate. Where our sun will live for 10 billion years, these giants may last only a few million, but they live brilliantly. They are the dazzling blue-white jewels of the night sky, forging not just helium from hydrogen or carbon from helium, but a whole sequence of heavier and heavier elements in their cores. Carbon becomes neon, neon becomes oxygen, oxygen becomes silicon, and finally, in the last desperate moments of the star's life, silicon fuses into iron. And with the creation of iron, the star's fate is sealed in the most catastrophic way imaginable. Iron is a cosmic dead end. Fusing iron atoms does not release energy, it consumes it. The star's core, which for millions of years had been a source of explosive, outward-pushing power, suddenly becomes an energy sink. The fire goes out, instantly. In less than a second, the outward pressure from fusion vanishes. Gravity, which had been held at bay by a raging nuclear furnace, now faces no opposition. The result is not a collapse, it is a cataclysm. The star's iron core, more massive than our sun, implodes upon itself at a quarter of the speed of light. The core temperature skyrockets to 100 billion degrees. The outer layers of the star, suddenly finding nothing beneath them, begin to plummet inwards, crashing down onto the collapsing core. They hit this incredibly dense, rebounding core and bounce back, creating a shockwave of unimaginable power. This shockwave, supercharged with a blast of ghostly particles called neutrinos, rips through the star from the inside out, tearing it apart. This is a supernova, the most powerful explosion the universe has known since the Big Bang itself. In a single brilliant flash, the star releases more energy than our sun will in its entire lifetime. It is in this crucible of destruction that the heaviest elements of the universe are forged. The gold in our jewelry, the silver in our electronics, the uranium in our power plants, all of it is created in the death throes of a massive star and scattered across the galaxy by the supernova's blast wave. We are quite literally made of stardust from these explosions. But what of the core? What is left behind after this cosmic detonation? For some massive stars, the imploding core is halted by a force even stronger than electron degeneracy pressure. The crush is so intense that electrons and protons are squeezed together to form neutrons. The entire core becomes a city-sized ball of pure neutron matter, a neutron star, an object so dense that a sugar cube-sized piece would weigh more than all of humanity combined. It is a new state of matter held up by neutron degeneracy pressure, but for the true titans of the cosmos, the stars born with the most extreme masses, even this is not enough. The gravitational pull of the collapsing core is so overwhelming, so utterly mind-bendingly powerful that nothing can stop it. Not electron pressure, not neutron pressure, not any known force in the universe. The collapse is total. It is absolute. The core continues to shrink past the size of a city, past the size of a mountain, past any physical dimension we can imagine, crushing itself down to a point of zero volume and infinite density. A singularity. Here, at this single infinitesimal point, the laws of physics as we know them break down completely. The star has not just died, it has been erased from space-time, leaving behind only its impossibly powerful gravitational field. It has torn a hole in the fabric of the universe. It has become a black hole, and so we arrive at the ultimate battleground. It is not merely a contest between two types of stellar remnants. It is a fundamental conflict fought on the very stage of existence, the fabric of space-time itself. Imagine this fabric as a vast, stretched rubber sheet. According to Einstein's theory of relativity, every object with mass creates a dip, a curvature in this sheet. This curvature is what we feel as gravity. A planet like Earth creates a gentle well. We are held in orbit around the Sun because we are rolling along the edge of the deep depression our star makes in the cosmic fabric. A white dwarf with the mass of a sun packed into the volume of a planet creates a far deeper and steeper gravitational well. It is a profound distortion of the local universe, a gravitational trap from which it is incredibly difficult to escape. Its influence warps the path of light that passes nearby, a testament to its extreme density and power. It is matter solidified and defiant, holding its shape and form and imposing its will on the geometry of the space around it. But the black hole plays a completely different game. It does not just create a steep well in the fabric of space-time. It creates a bottomless pit. It punches a hole clean through. The singularity at its center represents a point where the curvature of space-time becomes infinite. It is a place where space and time are so profoundly warped that they effectively switch roles. Surrounding this singularity is a boundary, a one-way membrane known as the event horizon. This is not a physical surface you could touch, but rather the ultimate point of no return. It is the shore of a river that flows in only one direction into the heart of the singularity at the speed of light. Once you cross the event horizon, escape is impossible. To leave you would need to travel faster than light, a violation of the most fundamental speed limit in the universe. Everything that crosses this threshold, light matter information, is lost forever, pulled into the central point of infinity. The white dwarf, for all its density, is still a part of our universe. You could, in theory, visit one orbit, study it. It is an object times in time-space. The black hole is something else entirely. It is an object that has times consumed times-space. It is the final chilling answer to what happens when gravity, the universe's most patient and persistent force, is allowed to win decisively, utterly, and without any opposition. So we stand at a cosmic crossroads, faced with these two fates. One, a triumph of matter where quantum laws erect an unbreakable shield against the finality of gravitational collapse. The other, a triumph of gravity, where the very rules of reality are rewritten into a single terrifying law of inevitable descent. Our journey from here will take us to the edge of both these worlds. We will explore the strange crystalline interiors of white dwarfs and probe the bewildering physics of the event horizon. We will witness what happens when these two cosmic titans meet, when a white dwarf finds itself caught in the gravitational snare of its more powerful, more mysterious sibling. Which force truly defines the end? The stubborn structure of matter or the infinite pull of the abyss? The answer lies ahead in the heart of the ultimate gravity battle. Across the unfathomable darkness of the cosmos, an ancient and silent war is being waged. It is a conflict without armies, without malice, fought on battlefields a billion light-years wide. This is not a struggle of empires or ideologies, but a far more fundamental contest written into the very fabric of existence itself. It is the eternal battle between creation and collapse, between the outward blaze of energy and the inexorable inward pull of gravity. Every star you have ever seen, every glimmer in the night sky, is a testament to this delicate, violent stalemate. And in the final, desperate moments of a star's life, this war reaches its most spectacular and terrifying crescendo, forging the most extreme objects in the universe. To understand them, you must first understand the battlefield and the titans that clash upon it. Our story begins, as all cosmic stories do, in the cold and the dark. Imagine a vast, ethereal cloud of hydrogen gas and interstellar dust, a stellar nursery hundreds of light-years across. It drifts through the void, a serene and seemingly permanent fixture of the galactic landscape. But it is not at peace. A silent, patient predator stalks this cloud. That predator is gravity. It is the universal architect and the ultimate destroyer, a force that works not through sudden violence but through relentless cumulative persuasion. Infinitesimally, it pulls on every single atom, urging it closer to its neighbors. Over millions of years, this gentle whisper becomes a command. The cloud begins to fragment, collapsing in on itself into dense, spinning knots of matter. As these clumps of gas, these protostars, grow more compact, the pressure at their centers begins to skyrocket. The cosmic vice tightens. Particles are smashed together with ever-increasing ferocity, and with pressure comes unimaginable heat. The core of the protostar climbs from freezing cold to millions of degrees. It is here in this crucible of gravity's making that the rebellion begins. A new force awakens. At a critical threshold of 15 million degrees Celsius, something miraculous occurs. The crushing pressure ignites the very heart of the star, triggering the engine of nuclear fusion. Hydrogen atoms, the most basic building blocks of the universe, are violently fused together to create helium. This is not a gentle process. It is a continuous, self-sustaining thermonuclear detonation. Each fusion reaction unleashes a colossal burst of energy in the form of photons, particles of light. This energy, this light, creates an immense outward radiation pressure, a stellar wind that pushes back against the relentless grip of gravity. The star is born. It settles into a long and stable adulthood, a phase scientists call the main sequence. For billions of years, it exists in a state of exquisite, perfect equilibrium. Think of it as a gravitational siege held at bay by a thermonuclear fortress. Gravity, the great compactor, tirelessly tries to crush the star into a single point. Fusion, the great expander, furiously pushes outward, providing the structural integrity to resist. Our own sun is in the midst of this grand stalemate right now, a shining example of this cosmic balancing act. For the past 4.5 billion years, it has converted 600 million tons of hydrogen into helium every single second, releasing an amount of energy that is for us almost incomprehensibly vast. This stable, light-giving period is what allows for the possibility of life for the long, slow evolution of planets and the beings that might inhabit them. But this stability is an illusion. The fortress is powered by a finite fuel supply, and the besieging army of gravity never ever rests. The fate of a star, its life story, and its ultimate demise is preordained from the moment of its birth. It is all decided by one single factor, its mass. The more massive a star, the more immense its gravitational pull, and the more furiously it must burn its nuclear fuel to fight back. These celestial titans live fast and die young, blazing through their hydrogen reserves in just a few million years before exploding in cataclysmic supernovae. We will journey into that heart of violence later. But for now, our story follows the quieter, more common, and in many ways more mysterious path taken by the universe's silent majority. Stars like our Sun, and those up to about 8 times its mass, face a different kind of ending. Their war with gravity is a longer, more drawn-out affair, a slow surrender that gives rise to one of the most bizarre states of matter imaginable. After 10 billion years of steady radiance, the core of a sun-like star will have fused nearly all of its hydrogen into helium. The thermonuclear furnace begins to sputter. With the outward push of fusion faltering, the stalemate is broken. Gravity, ever patient, begins to win. It squeezes the now inert helium core, compressing it mercilessly. This compression causes the core's temperature to soar once again, but this time the heat has a different effect. It radiates outward into the star's surrounding layers, which still contain unburnt hydrogen. This new wave of heat ignites a shell of hydrogen fusion around the collapsing core, a desperate final flaring of the star's power. The energy unleashed is more intense than anything from its main sequence life. This outpouring of energy inflates the star's outer layers like a monstrous balloon. The star swells into a red giant. Its surface cools and reddens as it expands, but its total luminosity increases 1,000-fold. It becomes an entity so vast it would swallow Mercury, Venus, and perhaps even our own Earth. This is the future that awaits our solar system. The gentle, life-giving sun we know will one day become a bloated, terrifying giant, its outer atmosphere grazing the orbit of Mars. This is not a peaceful retirement. It is a star in its death throes, raging against the dying of its own light. Inside this celestial behemoth, the battle continues. The crushing weight of the star's outer layers continues to squeeze the helium core, driving its temperature and pressure to even more extreme levels. Eventually, at 100 million degrees, a new fire is lit. The helium ash itself ignites, fusing into heavier elements like carbon and oxygen. The star has found a temporary reprieve, a new fuel source to push back against gravity's advance. But this too is fleeting. The energy from helium fusion is less efficient, and this new phase of stability lasts for only a fraction of the star's life. Once the helium is exhausted, the core is left with carbon and oxygen ash. For a star of this size, the story ends here. It simply doesn't have enough mass, enough gravitational might, to ignite the carbon and oxygen into even heavier elements. The fusion engine shuts down for the last time. The rebellion is over. Gravity has finally, it seems, won the war. Without any outward pressure to support them, the star's outer layers become unbound. They drift away from the core in a series of gentle pulses, creating one of the most beautiful and ephemeral spectacles in the cosmos, a planetary nebula. It is a misnomer having nothing to do with planets. It is the star's final graceful exhalation, a ghostly shroud of incandescent gas expanding out into the void. These intricate glowing structures are the star's legacy, seeding the interstellar medium with the heavier elements forged in its heart, elements that will one day form new stars, new planets, and perhaps new life. And at the center of this expanding celestial ghost, something remains: the victorious core. A searingly hot, incredibly dense ember left behind after the star has shed its skin. This is a white dwarf. It is the compressed, still glowing corpse of a star like our Sunday. And it is here that our understanding of reality is stretched to its breaking point. A white dwarf is an object of profound contradiction. It typically contains about 60% of the star's original mass, a celestial body heavier than our Sun, but it has been crushed by gravity into a sphere no larger than the Earth. The density is staggering, almost beyond human conception. A single teaspoon of white dwarf material, if you could somehow bring it to Earth, would weigh more than 15 tons. A sugar cube of this substance would outweigh an elephant. On its surface, the pull of gravity is hundreds of thousands of times stronger than what you feel on Earth. It is a crystal sphere of carbon and oxygen, a diamond the size of a planet, slowly over trillions of years, radiating away its residual heat until it becomes a cold, dark cinder known as a black dwarf, fading into the eternal night. Here, it would seem the story should end. Gravity has crushed a star into a planetary tombstone. The war is over, but it is not. In the subatomic realm of the White Dwarf, a final, desperate, and truly bizarre form of resistance holds the line. The final victory of gravity is thwarted by a force born not from heat or fusion, but from the fundamental rules of quantum mechanics. As gravity tries to crush the white dwarf even smaller, it smashes atoms together with such violence that their constituent parts are broken. The electrons are stripped from their atomic nuclei, forced to exist as a free-roaming, supercompressed sea of particles. This state of matter is called degenerate matter. And it behaves in ways that defy all classical intuition. In our everyday world, you can always squeeze things a little tighter, but in the quantum realm there are rules. One of the most fundamental is the Pauli exclusion principle. This principle, a cornerstone of modern physics, states that no two identical particles, in this case electrons, can occupy the exact same quantum state at the same time. You can think of it as a rule of ultimate personal space. Each electron demands its own unique energy level, its own subatomic address. In the hypercompressed core of a white dwarf, all the low-energy states are quickly filled up. As gravity tries to squeeze the electrons even closer, to force them into states that are already occupied, the electrons resist. They have nowhere else to go. This refusal generates a powerful outward pressure. It is called electron degeneracy pressure. This is not a force in the conventional sense like electromagnetism. It is a quantum shield, a collective defiance born from the very nature of matter itself. It is the universe's last line of defense against total gravitational collapse for stars of this size. This quantum pressure is astonishingly powerful, capable of supporting the weight of a sun and holding gravity at a final permanent stalemate. For decades, this was thought to be the end of the story for small stars. A quiet, quantum-supported retirement into eternal darkness. But in 1930, a brilliant 19-year-old Indian physicist named Subramanian Chandrasekhar was making the long sea voyage from India to study at Cambridge University in England. During the journey, he passed the time by contemplating the physics of these strange white dwarfs. He decided to combine the new theories of quantum mechanics with Einstein's equally new theory of special relativity, something no one had properly done before. He was exploring what would happen to the electrons in a white dwarf if the star's mass were to increase. According to his calculations, as you add more mass, gravity squeezes the core harder. To push back, the degenerate electrons are forced into higher and higher energy states, moving faster and faster. This is where relativity entered the picture. Einstein had shown that there is an ultimate cosmic speed limit, the speed of light. As the electrons in the white dwarf are pushed closer and closer to this limit, strange things begin to happen. Their resistance, their degeneracy pressure, no longer increases as effectively. They were pushing back with almost all their might, but the crush of gravity just kept growing. Chandrasekhar's mathematics revealed a shocking and terrifying conclusion. There was a tipping point. A precise critical mass beyond which the quantum shield of electron degeneracy pressure would catastrophically fail. He calculated this mass to be approximately 1.44 times that of our Sunday. Below this limit, a white dwarf could support itself forever. But if a white dwarf could somehow accrete more mass and exceed this limit, the electrons already moving at nearly the speed of light would be unable to provide any additional pressure. Their defiance would be broken. Gravity's victory would become absolute and total. The star would face a final, unimpeded collapse from which nothing, not even the fundamental rules of quantum matter, could save it. When he arrived in England and presented his findings, the scientific establishment, led by the eminent astronomer Sir Arthur Eddington, was dismissive, even hostile. The idea was too radical, too absurd. Nature, Eddington argued, would surely not allow a star to simply collapse in on itself to an unknown fate. But Chandrasekhar's mathematics were flawless. He had uncovered a fundamental truth, a line drawn in the cosmic sand. This boundary, now known as the Chandrasekhar Limit, is one of the most important numbers in all of astrophysics. It is the dividing line between a quiet afterlife and a truly violent end. It is a death sentence written into the laws of physics. It revealed that for the most massive stars, the battle against gravity was far from over. It was just entering its most brutal and world-shattering phase. The discovery of this limit opened a door to a new kind of physics, a new kind of stellar object, and a new kind of cosmic horror. It begged a terrifying question: if the quantum shield can break, what lies on the other side of the collapse? What happens when gravity finally and truly wins? But that delicate balance, that hard-won stalemate we witnessed in the heart of a dying sun, is not the only possible outcome in this cosmic war. The universe in its infinite variety forges champions of a completely different order. We have been exploring the lives of average stars, stars like our own sun, which fight gravity to a draw, leaving behind a dense, crystalline ghost, the White Dwarf. It is a testament to the stubborn power of quantum mechanics, a declaration that matter will not be crushed without a fight. Yet for every million of these stellar foot soldiers, there is a king, a titan. A star born into such immense mass, such overwhelming gravitational potential, that its life and death unfold on a scale almost beyond our comprehension. To understand the black hole, you must first understand the behemoth. Forget the gentle, steady glow of a sun-like star. Imagine instead a celestial blast furnace, a star born with 8, 10, 20, even 100 times the mass of our Sunday. These are the incandescent monarchs of the cosmos, the O-type and B-type stars blazing with a fierce blue-white light that scours their stellar neighborhoods with ultraviolet radiation. They are not merely bigger, their entire existence is fundamentally different. Their immense mass generates a crushing gravitational pressure at their core, a pressure so extreme it accelerates their metabolism to a fever pitch. While our sun will leisurely burn through its hydrogen for 10 billion years, these giants exhaust their primary fuel in a mere flicker of cosmic time, sometimes in as few as 10 million years. They live fast, die young, and leave a universe-altering corpse. Inside their churning hearts, the story of fusion plays out with violent speed. Where a sun-like star's journey ends with the forging of carbon and oxygen, for these titans that is just the beginning of the end. The core temperature and pressure are so colossal that fusion's alchemy continues relentlessly up the periodic table. Carbon fuses into neon, neon into oxygen, oxygen into silicon. Each stage of this desperate layered burning happens faster than the last, a frantic race against the ever-tightening grip of gravity. The star develops an onion-like structure with shells of different elements, fusing around a progressively heavier, hotter, and denser core. For a few thousand years it burns carbon, for a year neon, for a few months oxygen, and for a single final day silicon. In that last furious day, the star's heart forges the ultimate element, iron, and with iron the story changes forever. Up to this point, every fusion reaction in the star's core has been exothermic. It has released a torrent of energy, creating the outward pressure that holds the star up against its own weight. It is a cosmic engine running on the principle of converting mass into energy, the very equation that defines a star's life. But iron is different. Iron is the most stable atomic nucleus. To fuse iron atoms together into something heavier does not release energy, it consumes it. Iron is not fuel, it is ash. It is the final unburnable waste product of a star's life. The moment the core becomes dominated by iron, the engine at the center of this celestial giant, the engine that has raged for millions of years, sputters and dies. In an instant, there is no more energy pushing out. There is only gravity pulling in. And what happens next is not a gentle contraction, but the most catastrophic and rapid collapse known to physics. Gravity, the patient predator that has been squeezing this star for its entire life, finally wins. And it wins absolutely. The iron core, an object already as dense as a white dwarf, but many times more massive and hotter than the surface of our sun, loses its last line of defense. In less than a second, a single violent heartbeat, the star's core, once thousands of kilometers wide, implodes upon itself. Material from the star's outer layers begins to freefall inwards, accelerating to over a quarter of the speed of light, a Niagara Falls of stellar plasma, plunging into an infinitely small point. The core collapses until it is crushed past the point of electron degeneracy, the very force that holds up a white dwarf. The pressure is so immense that electrons are violently rammed into protons, creating a sea of pure neutrons and releasing a flood of ghost-like particles called neutrinos. The core has become a proto-neutron star, an object so dense that a single teaspoon of its material would weigh more than every mountain on Earth combined. This entire transformation from an iron core the size of a planet to a neutron ball just a few kilometers across takes mere milliseconds. The infalling outer layers of the star, traveling at unimaginable speeds, smash into this newly formed, unyielding surface of neutron matter, and they bounce. This colossal rebound creates a shockwave of unimaginable power. A sonic boom that rips outward from the core, supercharged by the blast of neutrinos that erupts from the neutron star's formation. This shockwave is the trigger. It is the detonator for the star's final act. A core collapse supernova. The explosion tears the star apart in a conflagration so brilliant it can outshine its entire host galaxy. A single point of light blazing with the energy of 100 billion suns. For a few weeks, it is the brightest object in the universe. In this terrifying crucible, all the heavier elements of the cosmos are forged. The gold in your jewelry, the silver in your coins, the uranium in our planet, they were all created and seeded across the galaxy in the death throes of a star like this, a tombstone and a cradle all in one. But after the light fades, after the beautiful expanding nebula of gas and dust thins out, our attention returns to the center. What is left of the core? What became of that stellar remnant? Here, the ultimate battle of gravity reaches its final turning point, and the star's initial mass dictates its ultimate fate. If the core left behind is less than about 3 times the mass of our sun, the collapse is halted by a new quantum force neutron degeneracy pressure. The neutrons packed shoulder to shoulder refuse to be crushed further. They create a neutron star, a city-sized atomic nucleus, spinning hundreds of times a second, an object even more extreme than a white dwarf, but still fundamentally a stalemate. Gravity has been held at bay once more. But what if the original star was even more massive? What if the remnant core it leaves behind is greater than that crucial limit, greater than 3 solar masses? Then there is nothing. No known force in the universe can stop the collapse. Not electron degeneracy. Not neutron degeneracy. Nothing. The core, that tiny, impossibly dense sphere, continues to shrink. It collapses past the point of being a neutron star. It collapses and collapses and collapses forever. Gravity is no longer just a force shaping an object. It is the object itself. The matter is crushed out of existence, leaving behind only its gravitational ghost. The the star has fallen into itself, puncturing a hole in the very fabric of space-time. It has become a black hole. Here, the contrast with a white dwarf becomes absolute. A white dwarf is a physical object. You could, in theory, stand on its crystalline surface, though you would be instantly flattened. It has a size, a volume, a temperature. It is the end point of matter that has successfully resisted gravity's final embrace. A black hole has no surface. It is not an object in the traditional sense, but a region of space, a gravitational prison from which nothing, not even light, can escape. It is gravity's ultimate victory. This prison is defined by a boundary, a one-way membrane known as the event horizon. The event horizon is not a physical barrier you could touch or see. It is far stranger. It is the point in space where the gravitational pull becomes so immense that the escape velocity, the speed needed to break free, exceeds the speed of light. And since nothing can travel faster than light, the event horizon is quite literally the point of no return. Imagine a cosmic river flowing towards a waterfall. As you drift closer, the current gets faster. At first, you can easily paddle against it. Then it gets harder. Finally, you cross a line where the river is flowing faster than you could ever possibly paddle. You haven't hit a wall, but your fate is sealed. The event horizon is that line, and the river is space-time itself flowing into the black hole. For an outside observer watching you fall towards this abyss, something truly bizarre would happen. As you approach the event horizon, the intense gravity would stretch and slow down time itself. Your movements would appear to get slower and slower. The light signals from you would become redder and dimmer as they lose energy climbing out of the immense gravity well. From our safe vantage point, we would never actually see you cross. We would see your image frozen, fading for an eternity, plastered against the edge of that black circle. Your final moment from our perspective would last forever, but for you, the journey would be terrifyingly brief. You would cross the event horizon in an instant, feeling nothing special at that precise moment, and be drawn inexorably inward. And where do you go? Where does all that matter end up? Our current theories, Einstein's general relativity, point to an answer that defies all logic and intuition. They tell us that at the very heart of the black hole, all the mass of the collapsed star and everything that has ever fallen into it is crushed into a point of zero volume and infinite density, a singularity. This is not a place in the universe. It is a moment in time, the end of time for anything that falls in. Here our understanding of physics completely breaks down. The laws of gravity and the laws of quantum mechanics, the two great pillars of modern science, give contradictory answers. The singularity is a signpost, a warning from the universe that our best theories are incomplete. It is the point where our mathematics scream into the void, telling us we have reached the edge of our knowledge, so we are left with two profoundly different cosmic destinies. On one side, the white dwarf, the beautiful, enduring corpse of a common star. It is gravity contained. It is a sphere of exotic matter, a cosmic diamond held in a delicate quantum mechanical stasis, a monument to the forces that can successfully push back. It has a past, a present, and a long, cold future of fading into darkness. It is an ending we can more or less comprehend. On the other side, the black hole, the terrifying ghost of a celestial titan. It is gravity unleashed. It is not an object, but a consequence. A pure, naked curvature of space-time. An information abyss whose interior is forever causally disconnected from our universe. It does not cool down. It only grows. It is a gravitational gyroscope warping the cosmos around it, a stark testament to a battle where there was no stalemate, only absolute and total conquest. It represents not just the end of a star, but the end of space and time as we know them. One is a period at the end of a stellar sentence. The other is the page being ripped from the book entirely. We have now met our two champions, born from starlight and forged in pressure. The stubborn, crystalline remnant and the insatiable space-time vortex. One represents a victory for matter, the other a triumph for gravity. They exist at the opposite ends of stellar death, governed by fundamentally different physics and possessing wildly different dominion over the cosmos. But these objects do not exist in isolation. Our universe is a dynamic, interactive place. So the ultimate question must be asked: What happens when these two champions meet? What happens when a white dwarf, the unbreakable object, is drawn into the clutches of a black hole, the unstoppable force? The stage is set for a confrontation of cosmic proportions, a clash that will test the limits of physics and create some of the most extreme phenomena the universe has to offer. The final battle is about to begin. For millions, even billions of years, the waltz can continue in near-perfect harmony. Locked in a gravitational embrace, the white dwarf and its living companion star trace elegant repeating orbits through the void. From a distance, it appears as a scene of serene cosmic stability, a quiet celestial partnership. But if you were to draw closer, you would witness a far more sinister and desperate drama unfolding. You would see that this is not a partnership of equals. It is a prolonged, silent act of cosmic vampirism. The white dwarf, with its immense density and unforgiving gravity, has become a predator. Its gravitational field reaches out a ghostly, invisible hand and begins to pull at the outer layers of its companion. Great streamers of hydrogen and helium, the very lifeblood of the healthy star, are siphoned away. They do not fall directly onto the white dwarf's surface. Instead, they are drawn into a swirling incandescent vortex around the stellar remnant, a structure we call an accretion disk. This disk is a masterpiece of gravitational mechanics, a celestial whirlpool of stolen matter heated to millions of degrees. It glows with a fierce, ethereal light, a testament to the sheer violence of friction in this extreme environment. As particles of gas jostle and collide, they lose energy, spiraling ever inward, closer and closer to the white dwarf's surface. This is a slow, relentless process, a feeding that can last for eons. With every particle that falls, the white dwarf gains a tiny amount of mass. Drop by drop, atom by atom, the dead star grows heavier. Inside its core, a battle that was won long ago is silently reignited. The force holding the star up, the bedrock of its very existence, is something called electron degeneracy pressure. It is not a pressure you or I could ever experience. It is a purely quantum mechanical effect, a fundamental rule of the universe that says no two electrons can occupy the same state in the same place. Imagine trying to push your hands together. At the atomic level, it is the repulsion between the electron clouds of your atoms that prevents them from passing through each other. Now amplify that repulsive force by a factor of trillions upon trillions. This is the invisible scaffolding that supports a white dwarf against its own colossal gravity. It is a shield forged not from matter but from the laws of physics themselves. For a solitary white dwarf, this shield is eternal. Its victory over gravity is absolute and final. But in this binary system, the situation has fundamentally changed. The white dwarf is no longer a static monument to a star's past life. It is an active, growing entity, and the quantum shield that supports it is being pushed to its absolute limit. With every gram of matter it steals from its companion, the gravitational pressure inside the white dwarf intensifies. The star shrinks slightly, becoming even denser its core, compressed to a state that defies all earthly comparison. A single teaspoon of this material would now weigh more than a herd of elephants. The electrons are packed so tightly that they are moving at near the speed of light, their quantum rebellion, the only thing standing between stability and catastrophe. The question is, how much weight can this quantum shield bear? Is there a point where even the fundamental rules of the universe must break? The answer to that question was discovered not in a gleaming observatory but on the deck of a steamship crossing the Indian Ocean in 1930. A brilliant 19-year-old physicist named Subramanian Chandrasekhar, travelling from India to study in England, passed the long days at sea by pondering the fate of these dead stars. Using Einstein's new theory of relativity and the fledgling science of quantum mechanics, he performed a series of calculations. What he found was not just a curiosity, it was a cosmic death sentence. He discovered that electron degeneracy pressure, for all its power, is not infinite. There is a precise, immutable limit to the mass a white dwarf can have. If it grows beyond this critical point, the quantum shield will fail and gravity will win an instantaneous, overwhelming victory. That limit, which would forever bear his name, is the Chandrasekhar Limit. It is approximately 1.44 times the mass of our own Sunday. 1.44. It is one of the most important numbers in all of astrophysics, a figure that dictates the line between eternal stability and violent annihilation. Now look back at our binary system at our feeding white dwarf. The accretion disk glows a fiery halo of doom. The star has been accumulating mass for millennia, slowly, patiently inching its way toward that fatal number. It might now be 1.3 solar masses, then 1.35, then 1.4. The core of the white dwarf has become a celestial pressure cooker unlike any other. The density has soared to over 1,000 tons per cubic centimeter. The temperature, driven by the unimaginable compression, is climbing into the hundreds of millions of degrees. This is a realm where the laws of physics are stretched to their breaking point. The star is a bomb, a planet-sized bomb, and the fuse has been burning for 1 million years. The final grams of stolen matter rain down upon its surface. The white dwarf crosses the threshold, 1.44 solar masses. The Chandrasekhar limit is breached. In this moment, electron degeneracy pressure fails. The quantum shield shatters. Gravity, the patient, relentless enemy, finally asserts its ultimate dominion. The entire star begins to collapse inward, a catastrophic failure of its fundamental structure. But something incredible happens in the first fraction of a second of this collapse. The runaway compression triggers a new, even more violent process. The core of the white dwarf is composed primarily of carbon and oxygen, the inert ash from its former life as a star like our Sunday. Under normal circumstances, this ash cannot fuse. But these are not normal circumstances. The sudden violent spike in temperature and pressure from the collapse pushes the core past the ignition point for carbon fusion. A spark is lit in the heart of the dying star. This is not the gentle, stable fusion that powers living stars. This is a runaway thermonuclear conflagration. Because the matter is degenerate, it does not expand and cool itself off the way normal matter would. Instead, the heat from the initial fusion reaction spreads instantaneously, triggering more fusion, which releases more heat in a feedback loop of unimaginable power. A wave of fire, a thermonuclear flame front, is born deep within the star and begins to tear its way outward. It moves at a staggering velocity, thousands of kilometers per second, a significant fraction of the speed of light. In less than 2 seconds, this wave of detonation rips through the entire volume of the white dwarf. The star that took billions of years to form and die is utterly consumed by fire from the inside out. The energy released is stupefying beyond any human scale of comprehension. In that brief, terrible instant, the dying star unleashes more energy than our sun will produce in its entire 10 billion year lifetime. It becomes for a few short weeks as bright as an entire galaxy. It outshines billions upon billions of stable living stars. This is a Type Ia supernova. It is not the death of a massive star collapsing under its own weight. It is the catastrophic detonation of a stellar remnant pushed beyond its absolute limit. The white dwarf is not crushed into a black hole. It is not compressed into a neutron star. It is completely and utterly obliterated, annihilated. There is nothing left behind but a rapidly expanding cloud of superheated gas and newly forged elements. The explosion is so powerful that it creates vast quantities of heavy elements, including much of the iron in the universe, the very iron in the blood that flows through your veins. The building blocks of our world, of our bodies, were forged in the heart of these terrifying cosmic detonations. The companion star, the source of the white dwarf's demise, is brutalized by the blast wave. It is scorched, stripped of even more of its mass, and sent hurtling through space like a cannonball, a wounded survivor of a battle it unknowingly started. From our distant vantage point, we see a new, impossibly bright star appear in the sky where none was before. A guest star, as ancient astronomers called them, blazing with a cold, brilliant light. It is a spectacle of ultimate destruction, a final defiant roar from a star that refused to collapse into darkness. It lost the battle against gravity, but it did so by choosing self-destruction over submission. It found a way to fail that was in its own way a final, blinding victory of light over the abyss. Yet the story of this cataclysm does not end with its own annihilation. In a beautiful twist of cosmic irony, this act of ultimate violence has become one of our most delicate and precise tools for understanding the universe. The key lies in that magic number 1.44 solar masses. Because every white dwarf that triggers a Type Ia supernova does so at the exact same mass, the Chandrasekhar limit, the physics of the explosion, is remarkably consistent. Each one of these detonations releases a nearly identical amount of energy. They are, in essence, cosmic standard bulbs of a known wattage. Astronomers call them standard candles. Think of it like seeing a row of streetlights stretching down a long, dark road. You know that every bulb is identical, that each one has the same intrinsic brightness. The ones that are closer appear bright, while the ones far in the distance appear dim. By simply measuring how dim a streetlight appears, you can calculate with incredible precision how far away it is. Type Ia supernovae are our cosmic streetlights. When we spot one exploding in a distant galaxy, we can measure how bright it appears to us. Because we know how bright it truly is, we know its wattage, we can calculate the distance to that galaxy with an accuracy that was previously unimaginable. These stellar ghosts, in their final moments of explosive glory, have become the yardsticks we use to measure the cosmos. They are the survey markers that have allowed us to map the vast three-dimensional structure of the universe. And it was by using these very supernovae, these echoes of annihilated white dwarfs, that we made one of the most profound and startling discoveries in the history of science. In the late 1990 seconds, teams of astronomers were using Type Ia supernovae to measure the distances to the most remote galaxies, hoping to calculate how much the expansion of the universe was slowing down due to gravity. But they found something completely unexpected. The most distant supernovae were dimmer than they should have been. They were farther away than all our models predicted. The only way to explain this was if the expansion of the universe was not slowing down at all. It was accelerating. Some mysterious anti-gravitational force was pushing the fabric of space-time apart. We call it dark energy, and its discovery, which has completely revolutionized our understanding of cosmology, was made possible by listening to the death cries of white dwarfs. The light from these explosions, traveling for billions of years across the expanding void, carried a secret about the ultimate fate of our universe, a secret we could only decipher because of the predictable physics of their self-destruction. So, this is one possible outcome in the great gravity battle. A white dwarf pushed to the brink chooses annihilation over collapse. It is a spectacular end, a blaze of glory that seeds the cosmos with new elements and illuminates the darkest corners of space, allowing us to chart our place within it. It is a crucial tipping point, a demonstration of how a star can be utterly defeated by gravity, yet still avoid the final inescapable prison of a black hole. But this thermonuclear escape route is not always available. It requires a specific set of circumstances, a slow and steady accumulation of matter. What happens if the conditions are different? What happens if the quantum shield fails but the spark of fusion never has a chance to light the fuse? Annihilation, for all its violence, is not the only form of defeat. For when the fire fails to ignite, gravity has an even more terrifying victory in store. A final silent surrender into absolute darkness. The violence of that cosmic detonation fades its light, a phantom limb haunting the interstellar void for millennia. But that act of thermonuclear defiance, that spectacular final protest of a white dwarf pushed beyond its absolute limit, is not the only story of stellar death written in the heavens. In fact, against the grand tapestry of the cosmos, it is the exception. It is the fate of a stellar ghost reanimated only by a stolen life force. To find the universe's true leviathans, to witness gravity's ultimate victory, we must turn our gaze away from these resurrected embers and look instead to the giants that were destined for a different, far darker, and infinitely more profound conclusion from the very beginning. Imagine a star not like our sun, but one born into royalty, a celestial titan dozens of times more massive, a brilliant blue-white furnace that burns with a fury 1,000 suns could never match. Its life is not a long, gentle twilight, but a brief incandescent roar. Where our sun will leisurely sip its hydrogen fuel for 10 billion years, this giant gulps it down in a few fleeting million. It lives fast and dies young, and its demise is not a quiet fading but a cataclysm that will forge the very definition of extremity. Throughout its turbulent existence, this supergiant is a battlefield. Outward, The colossal pressure of nuclear fusion, a continuous series of stellar-scale hydrogen bomb detonations, pushes against the dying of the light. Inward, the relentless, crushing grip of its own immense gravity, a force so powerful it actively distorts the space-time around it. For millions of years, these two forces are locked in a titanic equilibrium, a cosmic arm wrestle on an unimaginable scale. As the star exhausts its primary fuel, it begins a frantic, desperate process of survival. It starts fusing heavier elements in its core, a nested doll of celestial alchemy. A shell of hydrogen fusion surrounds a core of helium. When the helium is spent, it ignites to form carbon and oxygen. Then, in a cascade of increasing heat and pressure, the star builds shells of neon magnesium silicon, each layer burning hotter and faster than the last. The star becomes a cosmic onion, each layer a different epoch of its life, each fusion process a more desperate and short-lived defiance of the inevitable. The final stage, the fusion of silicon, lasts for perhaps a single day. In the last 24 hours of its multi-million-year life, the star creates the element that will seal its doom: iron. For every element lighter than iron, fusion releases energy. It is an exothermic process. It powers the star, holding gravity at bay. But iron is different. Iron is cosmic ash. To fuse iron into heavier elements requires an input of energy. It does not release it. It is the end of the line. The moment the core of this supergiant becomes a solid growing sphere of iron, the furnace at the heart of the star is extinguished instantly. There is no gradual cooling, no gentle dimming. One moment, the silicon-burning shell is pouring energy into the iron core, and the next, that energy source vanishes. The outward pressure, the star's lifelong shield against its own gravity, disappears in less than a second. The consequences of this single moment are almost beyond comprehension. Imagine a skyscraper 100 miles high, and in a single silent instant every structural support, every girder, every rivet simply ceases to exist. What follows is not a demolition, it is an obliteration. The star's colossal mass, no longer opposed by the fires of creation, succumbs to the one force that has been waiting patiently all along. Gravity takes over, and it is absolute. The core, an iron sphere, already more massive than our Sun, begins to collapse under its own weight. The outer layers of the star, quadrillions upon quadrillions of tons of stellar plasma, now have nothing supporting them. They begin to fall inward. They accelerate to unfathomable speeds, reaching over a quarter of the speed of light, a celestial avalanche roaring toward the center. The star is dying not by exploding but by imploding. As the core collapses, its density and temperature skyrocket to insane levels. In a fraction of a second, the iron heart of the star, once the size of the Earth, is crushed down to a ball barely the size of a city. The temperature soars to over 100 billion degrees. At these energies, the universe itself begins to break down. The very atoms of iron, the most stable configurations of matter, are shattered. Intense gamma rays born from the heat of the collapse disintegrate the iron nuclei back into helium nuclei and neutrons, a process that voraciously consumes energy, stealing even more support from the imploding star and accelerating the catastrophe. The core is now a maelstrom of protons, electrons, and neutrons. The crush of gravity becomes so overwhelming that it forces these particles together. Electrons are slammed into protons with unimaginable violence, creating a sea of pure neutrons and a ghost-like wave of elusive particles called neutrinos. It is at this point that a new force, a final desperate line of defense, rises from the quantum chaos to challenge gravity's dominion. You will remember that a white dwarf is saved from total collapse by something called electron degeneracy pressure. It is a fundamental rule of quantum mechanics that says no two electrons can occupy the same quantum state in the same space. They refuse to be crushed together, creating a pressure that holds up the star. But in this collapsing supergiant, gravity is so powerful that it has already overwhelmed that defense. It has literally squeezed electrons out of existence by merging them with protons. Now, however, the newly formed neutrons are facing the same crisis. They too are subject to the laws of quantum mechanics. They resist being forced into the same state and location. This is neutron degeneracy pressure. It is monumentally powerful, far stronger than its electron-based counterpart, the universe's last and most robust shield against gravitational oblivion. For a brief critical moment, the collapse of the star's core is halted. It has been crushed down into an object of impossible density, a proto-neutron star, a solid ball of neutrons packed as tightly as an atomic nucleus. This sudden jarring halt is like hitting a wall made of space-time itself. The infalling outer layers of the star, which have been accelerating inward at a quarter of the speed of light, now slam into this newly formed, unbelievably rigid surface. The result is the single most powerful shockwave in the universe. This rebounding wave of energy, supercharged by a flood of neutrinos escaping the core, tears back out through the star. It meets the still infalling outer layers in a titanic collision that blasts the star's magnificent body to smithereens. This is a core collapse supernova, a Type II supernova. It is an explosion so luminous it can outshine its entire host galaxy, seeding the cosmos with the heavy elements forged in the star's life and death. Elements like the iron in your blood and the calcium in your bones. The spectacle is glorious, a final defiant firework display. But our focus remains on the corpse left behind in the heart of the expanding nebula. What becomes of that crushed core, that city-sized ball of neutrons? Here we arrive at one of the most profound crossroads in the cosmos, a fulcrum upon which the fate of matter itself is decided. The outcome is determined by a single simple parameter, the mass of the original star. Gravity's power is a direct consequence of mass. The more mass you have, the stronger the gravitational pull. The strength of neutron degeneracy pressure, however, is constant. It is a fundamental property of matter. It can resist a certain amount of crushing force and no more. This cosmic balancing act defines the stellar graveyard. If the progenitor star was on the lower end of the massive scale, say between 8 and 20 times the mass of our Sun, the implosion leaves behind a remnant core below a critical threshold. This threshold, known as the Tolman-Oppenheimer-Volkoff limit, is thought to be somewhere between 2 and 3 solar masses. Below this limit, neutron degeneracy pressure wins. It holds. The collapse is permanently arrested. What is left is one of the most bizarre and extreme objects we have ever discovered: a neutron star. Imagine our Sun, a star nearly 1 million miles across, crushed into a sphere no bigger than a city like London or Manhattan. A single teaspoon of its material would weigh billions of tons on Earth. It is so dense that it is essentially a single gigantic atomic nucleus, a solid ball of neutrons spinning hundreds of times per second, possessing a magnetic field trillions of times stronger than Earth's. It is the ultimate cosmic diamond matter, compressed to its absolute limit, held in equilibrium, a testament to the power of quantum mechanics standing firm against the tyrant of gravity. It is a monument to a battle won, a stable, enduring corpse. A white dwarf is a victory for electron degeneracy pressure. A neutron star is a victory for neutron degeneracy pressure. Both are a form of stalemate with gravity. But what happens if the original star was even more massive? What if it was 30, 40 or 50 times the mass of our Sun? When that star dies, the remnant core it leaves behind will be heavier. It will exceed that critical Tolman-Oppenheimer-Volkoff limit. And that is when we witness something entirely new. That is when we see what happens when the last defense fails. For a star born above this threshold, the story of its death takes a dark turn. The implosion begins in the same way. The iron core collapses. It is crushed down past the density of an atomic nucleus. Neutron degeneracy pressure rises up, screaming its quantum defiance. But this time it is not enough. The sheer weight of the collapsing material, the pure gravitational force of more than 3 solar masses concentrated into a microscopic point, is simply too much. The final wall breaks. The last shield shatters. There is nothing left in the known universe to stop the collapse. Gravity, now completely unopposed, becomes an infinite runaway force. The core doesn't just shrink, it vanishes. In a fraction of a millisecond, the remnant of the star continues to crush itself smaller and smaller and smaller still, from the size of a city to the size of a mountain to a marble to a grain of sand. The known laws of physics, the very rules that govern space and time, break down under these impossible conditions. Our mathematics yields only infinities. The core continues to collapse all the way down to a point of zero volume and infinite density, a singularity. The star has not just died, it has been erased from the universe, crushed out of existence by the weight of its own ghost. Around this point of infinite collapse, the gravitational field becomes so intense, so grotesquely powerful, that it tears the fabric of space-time asunder. It creates a one-way membrane, a surface of no return. This is the event horizon. It is not a physical surface you could touch, but a boundary in space itself. Once you cross it, all paths, all possible futures lead in only one direction, inward toward the singularity at the center. Not even light, the fastest thing in the universe, can escape. Space is flowing into the singularity faster than light can flee. The star has become a black hole. It is no longer an object times the universe. It has become a place where the universe itself comes to an end. A scar on the cosmos, a point of infinite surrender. So we are left with three distinct fates, three possible endings to the grand story of a star's life, each one dictated by gravity's influence. For the vast majority of stars like our Sun, the end is a quiet retirement into the gentle, stable glow of a white dwarf. A victory for electron degeneracy pressure, a compact corpse held in stasis for eons. For the giants of the cosmos, a more violent end awaits, culminating in a titanic supernova that forges a neutron star. A victory for the far more powerful neutron degeneracy pressure, an object of mind-bending density, a celestial spinning top. But for the true titans, the rarest and most massive stars in the universe, there is no victory. There is no stalemate. There is only absolute unconditional surrender. Gravity overwhelms every force that stands in its way, crushing matter beyond all recognition and breaking reality itself. It creates a black hole, an object that is less a tombstone for a dead star and more a portal to an unknown physics, a tear in the fabric of what is real. A white dwarf is the ghost of a star. A black hole is the ghost of space-time itself. It forces us to ask a terrifying and profound question. What truly happens inside that veil of darkness beyond that point of no return, where our science fails us and imagination is our only guide, and so the final line of defense is shattered? The stubborn refusal of matter, the quantum fortress of degeneracy pressure that held gravity at bay for trillions of years in a white dwarf, has been overrun. Where that valiant stand once held firm, there is now only surrender. Absolute unconditional surrender to a force that will not be denied. This is gravity's endgame, the chilling, silent victory lap of a fundamental force of nature achieving its ultimate potential. The result is not a star, not a world, not even a corpse of an object you could point to. It is a wound in the universe, a point of infinite density and zero volume, cloaked in an event horizon from which nothing, not even the ghost of a photon, can ever report back. For decades, this was a phantom, a monster lurking in the dense mathematics of Einstein's relativity. It was a theoretical possibility so extreme, so absurd, that even its discoverers recoiled. How could we possibly prove the existence of an object whose defining characteristic is that it cannot be seen? How do you hunt a shadow in the infinite dark? You don't look for the shadow itself. You look for the chaos it creates in its wake. You search for the wreckage left by a predator that consumes light. Imagine a cosmic hurricane, a vortex of unimaginable scale and fury. This is an accretion disk, and it is our first witness to the prosecution. As gas dust and the shredded remains of unlucky stars are pulled into the black hole's orbit, they don't fall straight in. Instead, they are ensnared in a spiraling dance of death. This material, accelerated to fractions of the speed of light, is compressed and superheated by incredible friction. It becomes a celestial blowtorch, a swirling platter of plasma, glowing fiercely, not at thousands but at millions of degrees. It shines brighter than entire galaxies, blasting out radiation across the electromagnetic spectrum, from radio waves to the most energetic gamma rays imaginable. All this fury, all this brilliant, violent light, is generated by matter on its final, desperate inward spiral. It is the universe's most luminous swan song, a death scream of matter broadcasting its own demise just before it crosses the point of no return. We see this cosmic wreckage everywhere we look. At the hearts of galaxies, we find quasars, beacons of such impossible brightness they outshine 1 trillion suns. The only engine powerful enough to drive such a cataclysmic output is matter being consumed by a supermassive black hole. Closer to home in our own Milky Way, we find star systems where a perfectly healthy, visible star appears to be orbiting nothing. It whips around an empty point in space at breathtaking speeds, locked in a gravitational embrace with an invisible partner. By tracking the star's frantic orbit, we can precisely calculate the mass of its unseen companion. When that mass is dozens or even hundreds of times that of our Sun, yet crammed into a space that is optically empty, there is only one suspect left on the list. We have found the black hole's gravitational footprint, a clear and undeniable sign of its presence. But these were still indirect clues, compelling circumstantial evidence of a hidden culprit. We could see the crime scene, the cosmic mess, but we could not see the perpetrator itself. The dream, the seemingly impossible goal, was to photograph the unphotographable, to see the abyss, to capture an image of a black hole's event horizon, the very edge of forever. This challenge is almost comically difficult. The supermassive black hole at the heart of our own galaxy, Sagittarius A star, is 4 million times the mass of our Sun. Yet from 26,000 light-years away, its event horizon appears in our sky, as small as a donut left on the surface of the Moon. No single telescope on Earth, no matter how powerful, could ever resolve an image so tiny. To achieve this feat would require a telescope not meters wide, but thousands of kilometers wide. It would require a telescope the size of our planet. So that is precisely what we built. The Event Horizon Telescope, or EHT, is not a single instrument but a worldwide collaboration, a planetary alliance of observatories. From the high Atacama Desert in Chile to the volcanic peaks of Hawaii, from the mountains of Arizona to the frozen expanse of the South Pole, radio telescopes were synchronized with atomic clocks of impossible precision. They were linked together to function as a single virtual Earth-sized mirror, a technique called very long baseline interferometry. For nights on end, this global eye stared unblinking into the heart of a distant galaxy, Messier, 87.55 million light-years away. Its target, a behemoth, a monster black hole 6.5 billion times the mass of our Sun. It didn't collect an image in the way a camera does. It collected a torrent of data, a deluge of radio waves from the glowing gas swirling around the black hole. So much data, in fact, that it couldn't be sent over the internet. Instead, petabytes of information were stored on hard drives and physically flown on airplanes from every corner of the globe to central processing centers. It was a planetary effort, a testament to human curiosity and cooperation on a scale as grand as the cosmic question it sought to answer. An international team of hundreds of scientists spent years developing algorithms, cleaning the data, and painstakingly stitching together the faint signals filtering out the noise of the cosmos and our own atmosphere. They were trying to reconstruct a picture from the faintest of whispers spoken 55 million years ago. And then, in the spring of 2019, the world saw it. It was not a picture of a black hole. That is impossible. It was a picture of its consequence. There, against a lopsided asymmetric ring of blazing million-degree plasma, was a perfect circle of pure black, a void, an absence. This was the black hole's shadow. It's the region of space where light from behind the black hole has been so warped and bent by gravity that it is deflected away from our line of sight, creating a silhouette. The glowing ring itself is a marvel of relativistic physics. Light from the gas swirling around the black hole is contorted into a fiery halo. Part of the ring appears brighter because the material on that side is moving toward us at nearly the speed of light, its light amplified by relativistic beaming. The darker side is the material racing away from us. We were not just looking at a picture of gas. We were looking at a direct visualization of space-time being twisted into a pretzel by unimaginable mass. There, in that single iconic image, was the final visual confirmation. The monster was real. Gravity in its most extreme form had finally been caught in the act. The battle was over the victor unmasked. But to truly appreciate the black hole's reign, seeing its shadow is not enough. You must also learn to hear its voice. Not a voice of sound traveling through air, but a voice of violence that speaks in the language of space-time itself. For a century, Einstein's theory of general relativity had told us that space and time are not a static stage on which the universe performs. They are a dynamic, active fabric, a four-dimensional entity called spacetime. Mass and energy tell this fabric how to curve, and that curvature tells mass and energy how to move. This is the essence of gravity. A planet orbiting a star is simply following the straightest possible path through the curved spacetime created by that star. The theory also made a far more exotic prediction. It predicted that if you were to violently accelerate truly immense masses, objects like black holes, you would create ripples in the fabric of spacetime. Not ripples times on time spacetime, but ripples times of time spacetime. The very geometry of reality would stretch and squeeze as these gravitational waves propagated outward at the speed of light. For decades, this idea remained purely theoretical, another seemingly untestable prediction from Einstein's brilliant mind. The effect was thought to be infinitesimally small, far too faint for our clumsy instruments to ever detect. A strong gravitational wave passing through you right now would stretch and squeeze your body by less than the width of an atomic nucleus. Detecting such a subtle disturbance seemed like trying to measure the change in distance between Earth and the nearest star to the accuracy of a single human hair. It was by any rational measure impossible, but humanity built the impossible. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is one of the most audacious and sensitive scientific instruments ever conceived. It consists of two identical L-shaped facilities, one in Louisiana and one in Washington state, separated by thousands of kilometers to rule out local interference like earthquakes or passing trucks. Each arm of the L is a 4-kilometer-long vacuum tube with the air pumped out to a pressure 1/trillionth that of our atmosphere. Inside these tunnels, a powerful laser is split, sent down both arms, and reflected back by near-perfect mirrors. When the two laser beams return to the corner, they are recombined. As long as the arms are exactly the same length, the light waves interfere with each other in a way that cancels them out, producing darkness at the detector. But if a gravitational wave passes through, it will momentarily stretch one arm of the detector while squeezing the other. This minuscule change, 1,000 times smaller than a proton, would be enough to knock the laser beams out of perfect alignment. The waves would no longer cancel completely, and a flicker of light would flash onto the detector. For years, the observatories listened in perfect engineered silence, waiting. On September 14, 2015, at 95045 Coordinated Universal Time, it happened. A signal arrived. It was not a flicker, but a shout. A clear, unambiguous tremor that first rattled the detector in Louisiana, and then 7 milliseconds later, the one in Washington. The signal was beautiful in its simplicity. It started as a low-frequency hum, and then, over the course of just 0.2 of a second, it swept upwards in frequency and amplitude. It was a rising tone, a chirp that ended abruptly in a final, powerful burst before fading back into silence. Computers immediately began to decipher the message encoded in this cosmic vibration. The story it told was one of almost unimaginable violence. Somewhere out in the distant universe, 1.3 billion years ago, two black holes had been locked in a gravitational death spiral. One was 29 times the mass of our Sun, the other 36. For eons they had orbited each other, drawing closer and closer, shedding vast amounts of energy as gravitational waves. In the final moments, they were whipping around their common center hundreds of times per second, their event horizons moving at more than half the speed of light. They were tearing the fabric of space-time into a maelstrom. Then they collided. They merged to form a single, larger black hole of 62 solar masses. If you do the math, you'll notice something is missing. 29 plus 36 is 65, not 62. In that final cataclysmic fraction of a second, 3 entire solar masses, the equivalent of incinerating 600,000 planets the size of Earth, did not become part of the new black hole. They were converted directly into pure gravitational energy, according to E equals mc squared. This energy radiated away as that final powerful burst of gravitational waves. For a fleeting moment, the power of this single merger, this one collision, was more than the power radiated as light by every star and every galaxy in the entire observable universe combined. It was the most powerful energetic event humanity had ever witnessed, and LIGO had heard it. We didn't see it with light, we felt it with gravity. We had opened a new sense, a new window onto the cosmos. It was like a deaf species suddenly being granted the gift of hearing, and the first sound we heard was the thunderous applause of two black holes annihilating each other. Since that first detection, LIGO, along with its European partner Virgo, has heard dozens more. We have heard the chirps of merging black holes of all sizes. We have even heard the sound of a black hole swallowing a neutron star whole, a final choked-off cry as the star was snuffed out of existence. Each detection is another nail in the coffin for any lingering doubt. These are not theoretical phantoms, they are real, they are common, and they are the undisputed champions of the universe's gravity battle. Where a white dwarf represents a stalemate, a negotiated truce between matter and gravity, the black hole represents total conquest. The evidence is now absolute and overwhelming. The eerie shadow cast against a ring of fire, a silhouette seen across 55 million light-years, shows us their form. The violent space-time screams of their mergers heard a billion light-years away tell us of their power. They are not just the winners of the contest, they have fundamentally changed the rules of the game. They bend light, they warp space, they distort time. They are the ultimate expression of gravity's supremacy, the final word in the cosmic argument that began in the heart of a dying star. Matter, for all its quantum trickery and resilient strength, ultimately kneels. Gravity, in the end, always wins. And so we return from the brink, from the edge of infinity and the heart of a diamond star. We have travelled across cosmic history, witnessing the birth, life, and spectacular death of suns, only to arrive at this profound cosmic schism. Our journey reveals that the universe is not governed by a single monolithic destiny, but by a delicate yet fiercely contested balance of power. At the center of this ageless drama, we find gravity, the master architect, and the ultimate destroyer, locked in an eternal struggle with the fundamental resilience of matter itself. The outcome of this war, we have learned, is predetermined from the moment of a star's conception. It is a fate written not in prophecy but in a single unchangeable number, its initial mass. This one variable, this simple measure of cosmic inheritance, acts as the celestial judge, jury, and executioner, deciding whether a dying star will find a quiet, glittering peace or suffer a complete and total collapse into oblivion. For the vast majority of stars, those that lived their lives with a measured grace, their end is a testament to the strange and wonderful laws of the quantum world. As their nuclear fires gutter and fade, gravity, sensing weakness, begins its inexorable squeeze. The star's core is crushed, its atoms savaged, their familiar structures shattered beyond recognition. But just as the abyss seems certain, an extraordinary new force awakens from the subatomic realm. The Pauli exclusion principle, a law stating that no two electrons can occupy the same state, transforms from an abstract rule into a tangible physical shield. The electrons, stripped from their atoms and packed into an impossible density, push back. They generate a colossal outward pressure, a degenerate bulwark that halts gravity dead in its tracks. This is not a battle won with fire or fusion, but with the fundamental stubbornness of quantum mechanics. The result is the birth of a white dwarf, a stellar ghost, a celestial ember, glowing with the residual heat of a life well lived. It is a monument to defiance, a city-sized diamond forged in the crucible of gravitational collapse, forever preserving the memory of the star it once was. It stands as proof that sometimes in the face of annihilation, matter can find a way to endure. Yet this victory is not universal. For the titans of the cosmos, the colossal blue giants that burn through their fuel with reckless abandon, a far darker fate awaits. When their lives end, they do not go quietly. They unleash a supernova, a final cataclysmic roar that can outshine their entire galaxy. And in the aftermath of this celestial detonation, when the dust settles, gravity returns to survey the wreckage. For these massive stars, the core that remains is too heavy, its gravitational pull too ferocious for even the quantum defiance of electron degeneracy pressure. The squeeze continues, crushing electrons into protons to form a core of pure neutrons, creating a neutron star, an object of even more unimaginable density. But for the true behemoths of the universe, even this is not enough. If the remnant core surpasses the final threshold, the Tolman-Oppenheimer-Volkoff limit, then nothing, absolutely nothing, can stop the fall. Neutron degeneracy pressure, the strongest repulsive force we know, buckles and fails. The very fabric of space-time, the stage upon which the cosmic drama unfolds, begins to tear. Here, in this ultimate act of gravitational supremacy, a black hole is born. It is not an object in the traditional sense. It is a region of space-time so warped, so violently curved, that it becomes a one-way street. The event horizon, its infamous point of no return, is not a physical surface you could touch, but a boundary of pure geometry, a waterfall in the river of time from which nothing can escape. Inside, all known laws of physics crumble. All the mass of the once mighty star is crushed into an infinitely dense, zero-dimensional point of the singularity. At this terminal, all of our science, all of our understanding falls silent. Gravity does not just win, it achieves a victory so total, so absolute, that it erases its victim from the observable universe entirely, leaving behind only a void, a silent, perfect sphere of darkness defined by its gravitational scream. Here, in this chilling endgame, matter is not just defeated, it is annihilated, its very existence, reduced to a property of warped geometry. White dwarfs and black holes, then, are not merely stellar remnants. They are the twin pillars of extreme physics, the two possible conclusions to the universe's grandest story. One represents matter's final triumphant stand, the other represents its ultimate unconditional surrender, and it is in their existence as the universe's most extreme laboratories that their true importance to us is revealed. A white dwarf is far more than a cooling ember. As we watch these ancient stars cool over billions of years, we are witnessing a process of cosmic crystallization. Their cores of carbon and oxygen, under pressures quadrillions of times that of Earth's, are slowly freezing into a solid crystalline lattice. They are, in the most literal sense, becoming galaxy-sized diamonds. By studying the rate at which they cool a process, we can measure through their subtle changes in color. We can test our models of exotic matter. We can probe the physics of phase transitions under conditions that are utterly impossible to replicate on Earth. These objects are cosmic time capsules, allowing us to accurately age star clusters, and by extension the Milky Way itself, providing a crucial anchor for the entire timeline of cosmic history. Furthermore, when a white dwarf is not alone, its story can take a violent turn. If it has a binary companion, its intense gravity can siphon material from the other star. As this hydrogen and helium accumulate on the white dwarf's surface, it can reach a critical point, a ticking time bomb of stolen mass. When it approaches the Chandrasekhar Limit, the absolute maximum mass that electron degeneracy pressure can support, it triggers a cataclysm. The entire white dwarf detonates in a Type Ia supernova, an explosion of such uniform and predictable brightness that we can use it as a standard candle to measure the vast distances across the universe. It was through observing these specific white dwarf-fueled explosions that we made one of the most profound discoveries in the history of science. The fact that the expansion of the universe is accelerating, driven by a mysterious force we now call dark energy. The quiet, stubborn defiance of a white dwarf therefore holds the key to understanding the ultimate fate of the entire cosmos. If white dwarfs are the laboratories of dense matter, then black holes are the laboratories of space-time itself. They are gravity made manifest, allowing us to test Albert Einstein's theory of general relativity in its most extreme and unforgiving domain. For a century, his equations have predicted the precise way a black hole should warp the space and time around it, how it should drag the fabric of the universe into a swirling vortex, a phenomenon known as frame dragging. For decades, this was pure theory, but now we can see it. We can observe the light from distant stars bending as it passes near a black hole, a gravitational lens that magnifies the universe behind it. We can see matter in accretion disks heated to millions of degrees, glowing in X-rays as it spirals toward the event horizon, its final scream before being swallowed by the silence. The Event Horizon Telescope has even given us a direct image of this boundary, capturing the shadow that a supermassive black hole casts upon the brilliant light of the matter falling into it. But the most revolutionary tool for exploring these gravitational behemoths is not light but gravity itself. With the advent of gravitational wave astronomy, we have for the first time been given ears to hear the universe. When two black holes locked in a deadly orbital dance finally merge, they release more energy in a fraction of a second than all the stars in the observable universe combined. This energy is not emitted as light but as powerful ripples in the fabric of space-time gravitational waves. Instruments like LIGO and Virgo are our cosmic seismometers, feeling these infinitesimal vibrations as they wash over the Earth from billions of light years away. Each detection is a symphony of space-time, a complex waveform that encodes the masses, spins, and violent final moments of the merging objects. By listening to these mergers, we are mapping the unseen population of black holes, confirming Einstein's predictions with breathtaking accuracy, and peering directly into the heart of gravity's most dramatic act. We are witnessing the very structure of reality shake, and in those vibrations we are reading the secrets of the cosmos. This brings us to the frontier, to the edge of our knowledge where the future of astrophysics is being written. The grand challenge, the ultimate quest inspired by these enigmatic objects, is to bridge the chasm between our two greatest scientific theories. General relativity, Einstein's masterpiece, perfectly describes the universe on the grandest of scales: planets, stars, galaxies, and the curvature of space-time. Quantum mechanics, on the other hand, is the undisputed ruler of the subatomic realm, governing the strange probabilistic world of particles and forces. Each theory is a monumental success in its own domain, yet they are fundamentally incompatible. They speak different mathematical languages and offer contradictory descriptions of reality. And it is precisely at the heart of a black hole's singularity and in the superdense core of a white dwarf that both theories are pushed to their breaking points. Here, in these places where immense mass is confined to an infinitesimal space, the universe is screaming at us that our understanding is incomplete. A black hole's singularity is a place of infinite density and infinite space-time curvature concepts that are nonsensical in physics. It signifies the breakdown of general relativity. To understand what truly happens there, we need a theory of quantum gravity, a framework that can describe the granular pixelated nature of space-time at the smallest possible scales. We need to unify the smooth geometric world of Einstein with the chaotic quantized world of the atom. This is not merely a theoretical exercise. It is a mission that will be guided by observation. Our next generation of instruments is designed specifically to probe these mysteries. The James Webb Space Telescope is already studying the atmospheres of planets orbiting white dwarfs, searching for biosignatures, and asking whether life could potentially arise in these ancient stable systems long after the parent star has died. Such a discovery would fundamentally change our perception of habitability. In the coming decades, the Laser Interferometer Space Antenna, or LISA, will take gravitational wave astronomy into space. This trio of satellites, separated by millions of kilometers, will form a detector of truly cosmic proportions, sensitive to the low-frequency gravitational waves emitted by the mergers of supermassive black holes that sit at the heart of galaxies. LISA will be our ear for the slow, ponderous waltz of these cosmic titans, allowing us to map the evolution of galaxies and the very structure of the universe with unprecedented fidelity. It may even detect the faint background hum of gravitational waves from the Big Bang itself, an echo from the moment of creation. Other telescopes, like the upcoming Square Kilometre Array, will survey the sky with unparalleled sensitivity, hunting for pulsars orbiting black holes. These cosmic clocks spinning neutron stars that emit beams of radio waves with astonishing regularity are the most precise gyroscopes in the universe. By watching their signals wobble and warp as they orbit a black hole, we can test the predictions of general relativity to the 15th decimal place, searching for the tiniest deviation that might hint at a new, more complete theory of gravity. The quest to understand these stellar remnants forces us to ask the most profound questions imaginable. Is information truly destroyed when it falls into a black hole, violating a core tenet of quantum mechanics, or is it somehow preserved on the event horizon, as suggested by the holographic principle? Will Stephen Hawking's prediction of black hole evaporation through Hawking radiation ever be observed, proving that black holes are not eternal prisons, but slowly leak their mass back into the universe over unimaginable timescales? If we could watch a white dwarf for trillions of years, would we see it finally cool, and fade into a black dwarf, a cold, dead crystal of degenerate matter, the final inert state of a star like our Sun. Answering these questions may require us to abandon our most cherished notions of space, time, and reality. It may lead us to theories like string theory or loop quantum gravity, which postulate extra dimensions of space, or that space-time itself is made of discrete, indivisible units. White dwarfs and black holes are not just the endpoints of stellar evolution, they are the signposts pointing the way toward this deeper, unified reality. They are the crucibles where we can forge a theory of everything, a single, elegant framework that can describe every force and every particle from the instant of the Big Bang to the final fading embers of the cosmos. And so our epic journey through the life and death of stars comes to a close. We have seen that the universe is a place of breathtaking violence, an exquisite beauty of unyielding laws, and astonishing creativity. The struggle between gravity and matter has sculpted everything we see, from the planets in our solar system to the great cosmic web of galaxies. In the quiet, crystalline glow of a white dwarf, we see a reflection of persistence, a monument to the power of the quantum world to hold back the darkness. In the terrifying silent void of a black hole, we confront the absolute power of gravity, a force capable of bending space, stopping time, and erasing matter from existence. They are the yin and yang of the cosmic endgame, two opposite, yet equally fundamental outcomes of the same stellar story. They challenge us, they inspire us, and they remind us that the universe is far more strange, more wondrous, and more mysterious than we can possibly imagine. The light from these dying stars and the silence from these gravitational voids travel across billions of years to reach us, carrying with them the clues we need to piece together the ultimate story of who we are and where we came from. The next chapter of that story is waiting to be written, and its secrets are locked away in the heart of a diamond star and at the edge of infinity. The quest to unlock them continues.